Okay, welcome to a new unit, electromagnetic radiation. This is the third unit out of 4 that we'll be looking at in Physics 30. And so what we're going to be doing is we're going to be putting a lot of the concepts that we learned in electric fields, electro and magnetic fields and forces into play. So Ørsted said that there would be an electric current would make a magnetic field, and Faraday said that a magnetic field would make an electric current. Maxwell, who is a student of Faraday's, he put these two ideas together. So Faraday developed Ørsted's, Maxwell put the two together, and he came up with the theory of electromagnetic radiation, the two halves being electro and magnetic, and then the radiation that happens from them. And so there's 3 really key points that we need to take away in this first lesson. The first one is that an electromagnetic wave is produced by either an accelerating charged particle, and if it's accelerating, we would have a force net. Okay, if it's constant or if it's suspended and we have no force net, then we don't have an electromagnetic wave. And the other one is it has to be a changing magnetic or a changing electric field. So we're looking at this part here, force magnetic or force electric, and these two pieces here, an electric field, or a magnetic field, okay? At any point on the wave, the electric field has to be perpendicular. Again, there's that clarifying term, perpendicular to the magnetic field. And EMRs are transverse waves because the direction of travel is perpendicular to the oscillation. So let's look at that in this diagram. But the big key here is EMR waves travel at the speed of light. So here's a new symbol, C, for the speed of light. It's 3 times 10 to the power of 8. You can see it written down in other pieces of work as 2.998 or 3.00, I think it's 65, I'm not quite sure. But we're going to look at 3.0 times 10 to the 8. And it's always in a vacuum or in air as well. And the reason that we declare that it's in a vacuum is because this is all happening in a theory. There's no interference from any other particles. There's no interference from any other charged ions. There's no interference from wind resistance. There's just no interference. And so we say that it's in a vacuum. And this is really important. We're going to investigate this concept in this bullet point as a whole lesson. The speed of EMR waves vary as they go through different mediums. And mediums is just different things. So like water or glass or air. And so what we're going to look at is this whole idea of it being a transverse wave. And so what we're looking at is we can see here, I'll use my black, we can see this line right here. And this is going to be the direction. Oops, I'll write it in my pen, I guess. This is going to be the direction of the wave, otherwise known as wave propagation. So if we see this word on another piece of information and we see wave propagation, that's the direction of the wave. So we've said that it's going this way. Okay? Now, when we look at this up and down motion here, like this, we're looking at these two pieces being perpendicular. Okay, so this is the direction that the wave is moving. And we can see that this one here, this in and out motion here, we could call this our magnetic field. Again, this is because it's perpendicular to the direction. So the direction is going like this, and the magnetic field is going like this. So we get our 90 degrees or our perpendicular. The other aspect is this piece here, where we could be looking at our Oh, it's not working. I'll just use my pen. At our electric field. Going again, here's perpendicular. It's perpendicular to the direction of motion. The magnetic field is perpendicular, so perpendicular this way or perpendicular this way, it's still perpendicular. And we're going to be looking at some new words. Now, the grade 11s just came out of Physics 20 where we looked at waves, but now we're going to just refresh our memory. When we go from crest to crest or trough to trough, we're looking at what's called one wavelength. This is one complete cycle of the wave. So it measures the distance between successive crests or troughs. The source is the accelerating charges or the changing electromagnetic fields. The medium is what it's traveling through, so maybe it's traveling through air or it's traveling from air through water and then it's coming out of glass. Wave propagation, there's that key word again, is that it's a wave direction of a wave. The frequency we've been introduced to, frequency we know to be this symbol, and it's equal to the number of waves in a specific point of time. Okay, so this hertz, this breaks down into the number of cycles per second. Okay, or another one is RPM. That's another common unit. And then a period is the time it takes for one wave to pass. And period is indicated by a capital T. So frequency is the inverse of a period, and a period is the inverse of a frequency. Okay? Time is, or period is measured in seconds, and frequency, because seconds, you can see it written this way. For a unit, you can see it written this way for a unit. You can see it written this way for a unit. You can see it written as cycles per second. Okay, there's several different ways. This one is the traditional unit, hertz. Okay, the EMR spectrum. We are familiar with the EMR spectra. We live in the EMR spectrum every day, and we do it in the color spectrum. And it's a very narrow portion of wavelengths. So this is really key. The shorter the wavelength, so remember lambda is the symbol for wavelength, the higher the frequency. Or the longer the wavelength, the lower the frequency. So the shorter the wavelength, I'll just demonstrate this to you. The shorter the wavelength, if this is our marking period, we can see that we've had 1, 2, 3, 4, 5, 6 wave cycles go through in this time period. Whereas if I did that same time period, but I made my waves bigger, this one here is actually only half of a wavelength. Okay, so the bigger the wavelength, the greater the distance from trough to trough or crest to crest, the lower the frequency, the less number of cycles in a certain given of time. Whereas if we have really short wavelengths, we have a short distance from crest to crest, we can get more wave cycles in that same time frame. And so what we're looking at here, this is the frequency, so something times 10 to the power of 16, we can see fits in the ultraviolet zone, and in about the times 10 to the 14, 15, this is visible light. Oops, visible light. Okay, this is something, this says memorize for the diploma. This is just strictly memorize. Memorize that the higher the frequency, the lower the wavelength. And that the lower the frequency, the bigger the wavelength. And we can see that here. Here is something times 10 to the power of 4, and it's got a wavelength of 3 times 10 to the power of 4. Whereas here, this has times 10 to the 24, so that's a very high frequency, and we see that it's 3 times 10 to the, probably about the negative 16 wavelength. So very, very, very small distance. Here's times 10 to the 4, and here's 0. Okay, so you can see the difference in a very short period of time. You do need to know radio waves have a very large frequency. So 93.1, which is the CJXX hertz, or Q99 is 98.9. Those are the frequencies, because FM stands for frequency and AM stands for amplitude. Okay? Microwaves, the ones that we love to heat our food into, operate in times 10 to the 8 to 10 to the 12. It's a little bit of overlap, but essentially infrared is times 10 to the 13-ish. Again, visible light, 10 to the 15. Ultraviolet, just outside. So before we hit infrared, we have, or just before we hit visible light, we have infrared. Right after visible light, we have ultraviolet. And the way to remember this is this ends in the word red, and our spectrum starts with red. This ends in violet, and our spectrum ends in violet. Okay, so infrared, red, orange, yellow, green, blue, indigo, and violet, and then ultraviolet. X-rays, and then gamma rays. And this I never really paid attention to. Gamma rays, until my husband had cancer and we were at the Cross Cancer Institute, and while he was in getting his MRI, there was this thing called gamma, that's the symbol for gamma, the gamma knife. And so I got inquisitive, because that's what I do, and a gamma knife is a precision tool where they inject or they use gamma rays and they target cancerous brain cells. Because in our brain, you know, if you go millimeters, less than millimeters, either side of something important, you can lose your sight, you can lose your hearing, you can lose your vision, you can lose your ability to talk, you can lose your ability to walk, and that's just by millimeters. So they go in with this gamma knife and they target very specific brain cells. It was so intriguing. It was probably the only positive that came out of Dwayne having cancer. Okay, monochromic light. Mono meaning one. It's a single frequency. So red is monochromic at 700 nanometers. And violet is monochromic at about 400 nanometers. Okay, so this is red, this is violet, and we spread those out in between. Well, here's the colors right here. Okay, white light is not. White light is not monochromic, because if we take a white light and we shine it through a prism, what do we see out the other side? We don't see white light. We see the rainbow. So white light is comprised of all of the wavelengths, whereas black is the absence of all of the wavelengths. Okay, so just remember this piece. White light is not monochromic because it has a bunch of the frequencies. There are lots of formulas that we're going to look at. So light, which is a type of EMR, right? Light in here. We have two different theories. There's the wave theory and the particle theory. So wave theory is that it travels, the light particles travel like this. Okay? And then there's the particle theory, or modern physics, or quantum physics, and we're going to touch a little bit about that in the next unit. But that light travels in little packets of energy called photons. And they travel through. Well, then we get this beautiful theory called the wave-particle duality, which means that these little packets of photons travel in a wave pattern. Okay? So EMR that has a frequency less than visible light is treated as a wave. Oops, this is waves. And anything greater than a frequency of visible light, so this side here, is treated as particles. But what they're saying is that these little packets of photons travel in a wave pattern. Okay? So we're going to look at the wave theory to start with, and then we're going to end off with the particle theory. All right, wave theory. The speed of the EMR wave, not the speed of light, but the speed of EMR wave, so speed of light, this is very specific, 3.0 times 10 to the 8 meters per second. Okay, so that's the speed of light for EMR in a vacuum or air, is equal to the frequency. So here's those two units I talked about, hertz or seconds to the -1, multiplied by the wavelength, and period, which is the time it takes one complete wavelength to happen, and frequency is the time it takes, it's the amount of cycles in 1 second. Okay, so this is period, the inverse is frequency is equal to 1 over period. You can do the rearranging to prove it to yourself. So since EMR travels at a constant speed as long as it remains in the same medium, this is so key. People forget this part. Remains in the same medium. Okay? We can use constant motion, velocity equals distance over time, where velocity is the speed of light and all EMR. So whether it's an infrared wave or an ultraviolet wave. D is the distance that the EMR traveled, and T is the time. So let's look at some questions. If a star explodes 9.85 times 10 to the 6 meters from Earth, how many days would it take light? Light is now code word for EMR. Okay, so when we're talking EMR, velocity is equal to 3.0 times 10 to the 8 meters per second from this explosion to reach Earth. So when we write down our givens, velocity is 3.0 times 10 to the 8 because it's EMR. The distance is equal to 9.85 times 10 to the 26 meters. And it's asking us how many days. So time is equal to what? What am I looking for? I'm not looking for distance. I'm looking for time. So we can see where seconds is the third, like the meters over seconds. So these are going to cancel out and it's going to become seconds as our unit. So I got, when I run it through my calculator, I get 3.28333 repeating times 10 to the 18 seconds. But the question asks us days. So 3.28 times 10 to the 18 seconds I want days. I have seconds. There are, let's do it this way. Let's do it in 2 steps. Days, let's do hours. Hours is easier. 3,600 seconds in 1 hour. And there's 24 hours in 1 day. So I'm going to go 3.28 times 10 to the 18 divided by 3,600, get an answer, divided by 24, and I'm going to get 3.80 because I'm looking at sig digs, which is 3, 1, 2, 3, times 10 to the 13 days. Okay? So I know that I can use velocity equals distance over time because it's remaining in the same medium. It's just going through the atmosphere. It's not going through anything else. If it changed, we would be looking at a different formula, and that's in about 5 lessons. Okay? Blue light has a wavelength of 460 nanometers, and red light has a wavelength of about 720 nanometers. Which color has more energy? Okay, well, this is 460 times 10 to the negative 9 meters. Nano is times 10 to the negative 9. And this is 720 times 10 to the negative 9 meters. Which one takes more energy? So we're going through the same amount of time. So we're going to say that blue light, because which one is, remember, frequency. If I increase my frequency, I'm going to have more energy. And so if I have an increased frequency, I'm going to have a shorter wavelength. And so blue light has a shorter wavelength Okay, if I have an increased frequency, I'm going to have an increase in my energy. It's moving substantially faster than red light at 720 nanometers. Okay, and then it says calculate the period of my blue light. So, pieces of information that I know, my wavelength is 460 nanometers, and there are, in 1 nanometer, there is times 10 to the negative 9 meters. So I'm going to get 4.60 times 10 to the negative 7 meters. Or you could leave it as 460 times 10 to the negative 9 if your brain works that way. Either way, they're equally correct. Okay? And what else am I given? Well, I know that it's asking us to calculate for the period. So let's start where we're looking. Period is equal to 1 over frequency. Do I have frequency? No, I don't. So how do I solve for frequency? Well, I just learned this beautiful formula where velocity is equal to frequency times wavelength. And so I know this because it's EMR, right? It's talking about light. It's EMR. So V is equal to 3.0 times 10 to the 8th. I'm looking for frequency, and my wavelength has been given to me. So frequency is equal to V over lambda. 460 times 10 to the negative 9. And I get, I need my calculator. Let me see. Calculator. Scientific. And I'm going to go 3. What? I can't do exponents on here. Times 10 to the power of that's not going to work. Anyways, you're going to get a value for this, and then I'm going to go back to period, and I'm going to get that value, and I'm going to go 1 divided by it. So I'm going to get 1 over all I've done here, I wrote 4.6 times 10 to the 7. That's the same as 460 to the power of -9. And I'm going to get 0.53 times 10 to the -15 seconds. Okay, 1.53 because I'm at 700 or 460 nanometers. I'm at 3 sig digs. This here, the way that this is written, 1 over something, is same as okay, if you don't see this, that's okay. This is legitimately what this is written as. 1 over the frequency. It's 1 over velocity over lambda. Okay, period is equal to. It's another way of looking at the formulas. Okay, if you're not all confused and you got this figured out, the math is not hard. The concepts are a little trickier. Work on page 189, questions 1 to 5, 9 through 11, and 14 through 19. And just because you have nothing better to do, there's going to be a homework check tomorrow. Okay? You guys have a great day.